Hi folks, it's a great day to do chemistry. I'm here today in this webcast to introduce potential energy diagrams. Potential energy diagrams are very useful for helping us to explain aspects of reaction kinetics. They also have applications in thermochemistry, so it's definitely something we need to talk about. I want to backtrack a little bit and discuss collision theory really briefly. All right. In order for reactions to occur, collision theory tells us that first the particles have to collide, all right? But that's not enough. Just colliding isn't sufficient. They have to collide with a particular orientation. And if they don't have that correct orientation when they collide, they're just going to separate and nothing's going to change, all right? And so that's what is shown here in this illustration. I've got two particles that are colliding. The first four orientations, the way that molecules are set relative to each other, nothing happens. Only when they collide in that fifth orientation do we actually get new materials forming, new molecules forming. Okay, and so what this orientation is different for every single reaction. You're not expected to know those for different reactions, but the idea that only certain orientations are going to actually lead to a change is an important idea. But that's not enough, all right? The other statement of collision theory tells us that not only must they collide with the right orientation, but they have to have enough energy to react. So when they collide, they need to be moving with enough kinetic energy to actually make the product, all right? So as an analogy, you can think about trying to roll a boulder over a hill. If you don't get that boulder moving quickly enough, you're not going to get over the hill and make your products on the other side, all right? This amount of energy that you need is referred to as the activation energy. Sometimes we'll write just E sub A. And it's the minimum kinetic energy that the particles have to have when they collide in order for the reaction to occur. So we have to have the right orientation and enough energy or nothing happens. The particles just separate and they go on their merry way as if they had never done anything. All right. When we think about potential energy diagrams, okay, we can think about the enthalpy of reaction, and we can represent that with our potential energy diagrams. But we can also talk about this activation energy piece. So what I've got here is a very simple potential energy diagram showing the reactants and then the products. Now, in this particular case, it's an exothermic reaction. The products are at a lower energy point than the reactants, okay? And the difference between them is the enthalpy of reaction. We always define this as the enthalpy of the products minus the enthalpy of the reactants. This would be a negative number because this is an exothermic reaction and energy is being released. All right, so the fact that the products are lower tells us it's exothermic. Okay, but we're also showing the activation energy on this diagram. Okay, and so that's what this second arrow is. It goes from the energy of the reactants to the top of that barrier. That's the amount of energy that we need to have when the particles collide in order for them to react. And if they're not moving with enough kinetic energy to get there, get over that barrier, they'll never make the products. All right, so it's from the reactants, I would say, to the top of the hill is the way to keep that in your memory. Okay. Now, we can also talk about the transition state. The reason the particles need to have this energy when they collide is that collision theory tells us that we have a transition state. All right, there's a high energy state where I'm breaking bonds and making bonds, and this is called the transition state or sometimes the activated complex. And if I don't have enough energy to put in to start breaking the bonds, I'm not going to be able to make this transition state. All right, and so in the particle level model, I'm trying to break up a bond between a pink atom and a red atom and trying to form a bond between a darker pink atom and sort of that raspberry atom. All right, I'm trying to make and break bonds. That's what happens at the transition state. This is really where all the interesting chemistry is happening. And if I don't have enough energy to get up there, I can't react. All right, it's a threshold. Either you have it or you don't. Okay, so we've got this transition state, which I'm trying to give you an idea of how this works. Again, the nature of the transition state is particular to that reaction. All right, now this diagram also helps us to see that we can find the activation energy for the reverse reaction. If we're going backwards, the products are now making reactants again in a reversible process. If I go from the energy of the products to the energy of the transition state, that gives me the activation energy for the reverse reaction. All right, so these are all things that you should be able to pull out of these potential energy curves. Okay. One of the other things I wanted to mention is that activation energy has a huge effect on reaction rates. If the activation energy is smaller, the reaction is going to go more quickly. And if the activation energy is larger, fewer particles are going to have that minimum. All right, they're not going to be moving quickly enough, and the reaction will be slower. It's sort of like a minimum passing grade on a test. If the minimum passing grade on a test is a 60, a high percentage of students will meet that minimum. But if the passing score is set at a 95, only a very small fraction of students would have that minimum, and we'd have a much smaller passing rate. And so we can think about it that way as a useful analogy. So, all right, if we look at these four potential energy diagrams, A, B, C, and D, all right, which one would we expect to be the fastest? Which one would we expect to be the slowest? Why? Well, what we really have to look at here are the activation energies for the four curves. All right, so I've put the arrows in, right? We just talked about this. The bigger the activation energy, the slower the reaction. The smaller the activation energy, the faster the reaction. And therefore, if we look at just the activation energies for A, B, C, and D, right, we would expect curve B, or process B, to have the slowest rate. It's got the largest activation energy. And we would expect D to be the fastest because it's got the smallest activation energy. We're not looking at the delta H for the process. We're looking at the activation energy. All right, now another important idea here that we can tie into our potential energy diagrams is a catalyst. All right, a catalyst speeds up a reaction rate without being consumed. It makes it go faster, but when you're done, you get it back in its original form. All right, and so if we look at a potential energy diagram for a regular reaction, all right, we can measure the activation energy for that particular process. But if there's a catalyst, the activation energy is smaller. All right, now the energy of the reactants is the same. The energy of the products is the same. Delta H isn't affected here. It's the height of the energy it takes to get to the transition state is smaller. The activation energy is lowered by the presence of a catalyst. This one mentions it being an enzyme. Enzymes are biological catalysts. There are a lot of different kinds of catalysts. So what you need to really remember about a catalyst is that they effectively lower the activation energy, right? And because the activation energy is smaller, the reaction speeds up. They may actually change the process by which the reaction occurs. We call this the mechanism, right? Reactions can occur through a series of steps, and in some cases, the presence of a catalyst actually changes what the steps are to get from reactants to products. We're not going to go into mechanisms in this webcast, but it's a really interesting topic. And so those steps may change when we have a catalyst. So in this diagram, the red one shows the uncatalyzed reaction, which appears to occur in a single step. But the catalyzed reaction, which is shown in green, has the same delta H, but now it seems to appear in 3 steps. All right, but the activation energies are very low and the reaction's much faster. All right, and so we do get it back in its original form. Right, that's one of the hallmarks of a catalyst. Now there are different classes of catalysts. We can have homogeneous catalysts and heterogeneous catalysts. All right, so we can have catalysts that are in the same state of matter as the reactants. Your biological and catalysts, enzymes being the most common example. There's also catalytic RNA. Tom Cech won the Nobel Prize for that work. There's research into engineering antibodies and manipulating their structures so that they can catalyze reactions as well. And those would all be homogeneous catalysts. The reactants and the catalysts are in the same state of matter. But the catalytic converter in your car engine takes the exhaust gases, they deposit on a piece of platinum, right, that ends up catalyzing the reaction, the gases leave. That's a heterogeneous catalyst, where it's in a different state of matter, right? The catalyst is a solid and the reactants and products are gases. Now we can also have inhibitors. Inhibitors cause reaction rates to slow down because they inhibit the reaction, and these can be biological in nature as well. They may interfere with the enzyme active site or tie up the reactant in a complex so that it doesn't react. This is how food preservatives work, and they can be very interesting. There's a lot of interesting drug design and research going on in this area. All right. They're also really important in biological feedback mechanisms, your thyroid function. Right? You need to make those thyroid hormones to keep your metabolism going. Oh, no, you've got plenty. You need to stop it. All right. Inhibitors play a part in that, and also in the whole process of maintaining body temperature. Right? So these feedback loops are really important, and they involve inhibitors. But what I want you to know is that they cause reaction rates to slow down.